Good morning. My name is Samantha Riles from Sugar Research Australia, and I'd like to welcome you to our fourth and final milling webinar for 2020. Today, Dr. Heidi du Clou from Sugar Research Australia will be presenting on opportunities in near-infrared technology for our industry. Please note that today's webinar is being recorded and a copy of it and the slides will be sent to all registrants. Throughout the presentation, all attendees will be on mute. If you are having any technology issues, please send a message in the chat box, which is located on the menu bar of your webinar screen. If you experience any issues in hearing the sound coming from your computer, please feel free to join by phone, and I have put this number in the chat box. I will be assisting as a co-host to ensure that all runs smoothly. We encourage you to take an active part in today's webinar by asking questions. As this webinar is in listen-only mode, you can do this at any time throughout the webinar by typing your question into the Q&A button on the menu bar. At the end of the presentation, there will be an opportunity for Heidi to answer those questions. I'd now like to hand over to your presenter for today, Heidi. Thanks, Heidi.
Thank you, Sam, and good morning to everyone, and welcome to this webinar where I will be discussing some opportunities for our industry potentially to use NIR in future endeavours. I thought a good place to start would be to provide an overview of the current research that we are conducting at SRA, which incorporates NIR technology, and use that as a springboard to then discuss some of the advances that have occurred in the NIR space and what other industries are doing to tap into those advances, and potentially what we could start looking at doing to try and improve the sustainability or profitability of our industry using NIR. So the first project that I'm going to give an overview on is one of our RFU funded projects that started off last year in July. This particular project is aimed at developing calibrations to predict fibre quality measurements for clones in different growing regions in our breeding program. Now, fibre quality traits include things such as impact resistance, shear strength, as well as short fibre content. And these are important parameters because they are used to predict the potential milling characteristics of clones which will potentially be released. However, the current laboratory methods that we use to determine these traits are very labour intensive, and we only have one set of these equipment at our Bundaberg breeding station. What the plan is then is to look if we can enhance our current SpectraCane NIR calibrations with ones which could also predict these fibre quality traits in clones, and that will allow us to start determining these traits much earlier in our breeding program, and hopefully we can identify these sorts of traits earlier for selection. So before this project started, we at SRA had developed some preliminary fibre quality NIR calibrations at our Bundaberg station. Those preliminary calibrations involved about 500 samples that were processed through the SpectraCane as well as the FQM lab. And that was used to then target clones in the 2019 season that we would then include in building improved calibrations which could be used on our SpectraCane suites. So in 2019, the first year of this project, we processed an additional 1,557 samples through both the Bundaberg SpectraCane as well as the Bundaberg FQM laboratory. And from the table, you can see that we have now included not only the advanced stage trial clones, but also the clonal assessment trial clones. So earlier in the breeding program, we've been able to scan these clones to hopefully start predicting these traits. So here is an example of what the calibration spectra look like, or the calibration plots look like, after we've added the 2019 data to our initial calibration set. And the table below gives a calibration summary of all these statistics involved in developing these models to show that the standard error of calibration is quite good. And from this in particular, I can say the impact resistance standard error of calibration of 0.09 quite closely matches the standard error of the laboratory assessment, which is 0.1. And this was determined in a repeatability and reproducibility study that we did as part of this work in 2019. So that gives us confidence that we will get some sort of fair prediction when predicting back for impact resistance on any clones that are scanned through the Bundaberg NIR. What we then did was we updated all the NIR calibration suites on the different SpectraCane units throughout the breeding program, so throughout the regions. And we then reassessed the 2019 data against the calibrations to see how the distributions of clones differed in these FQ traits across the regions. The main take-homes from these box and whisker plots that show the distributions of these clones is that there exists significant differences between the clones at the different regions, which indicates the presence of bias. So although we can say that a constant bias relative to standards that are processed in the regions would not affect clonal assessment, we do want to investigate whether we can correct for this bias in the upcoming year. So in 2020, the plan is to process a further 1,500 samples from the various regions through the Bundaberg Fibre Quality Laboratory, as well as collect the data from the scans on the regional units and then use this to validate against the 2019 calibration, which has been updated. We're also including assessments of the bias by incorporating scanning of photometric standards at the beginning and end of each season. And on the right, we have an example of what a photometric standard scan looks like on the Bundaberg SpectraCane, with reflectance values ranging from 99.95% to almost zero. So eventually at the end of this 2-year project, the aim is to hopefully build robust fiber quality measurement NIR calibrations, which will be deployed across all the breeding SpectraCane units, so that we can then apply these assessments to all clones in the breeding program. So a second project that we have recently started up, which also uses NIR, is one which is looking at detecting Ratoon Stunting Disease in the mill. This particular project is funded by the RFU and partnered with UQ, and it's taking a dual approach to trying to determine whether we can get new detection methods for RSD. So in the first instance, our partners at UQ are looking at developing a molecular DNA method which can be used to test first expressed juice for any RSD DNA that may be present. And the second approach is where SRA is involved, is looking at developing NIR calibrations against the DNA assay with any of the NIR scans associated from the CAS system, or the cane analysis system in the same mill. Ultimately, what we hope to achieve with this project is that we will not only develop 2 new detection methods for RSD or disease in general, but that we can then start looking at mapping the incidence of the disease in our industry and then we can assess the economic impact of RSD. This will also allow us, however, to start looking at a targeted management approach to RSD to try and reduce the impact. And so we're quite excited about the progress we've already made, which I will now start looking at and discussing with you. So although this project only started off in January this year, as I say, we have made a significant amount of progress. Our partners at UQ have already developed RSD-specific primers, which can be used. So these are DNA-specific detection tools for the RSD. And they've also refined a technique which is quite simple and easy to follow, which allows the assay to be conducted on mildew samples. And here is a schematic of exactly that procedure that UQ have already developed. So what we've done already is we have tested 30 mildew samples from a mill from the 2019 season using this UQ-based assay. And from the results, 24 out of the 30 samples returned a positive RSD response. What we decided to do from there is to then correlate the mildew data with any of the NIR scans related to the cane rakes that pass through the mill related to those dew samples. So what we then did was looked at building a NIR classification model, which then allowed us to try and discriminate between scans within rakes that are potentially RSD positive based on the UQ DNA assay. What we found was if we assigned a 0 value to the results that were negative or disease-free results, they were represented by the blue dots in the plot, and we assigned a 1 value to those samples which returned a positive RSD result. We could then produce something like this linear discrimination plot, which is seen, which was processed using 5 principal components on the model. So from the 2,231 associated NIR scans with those 30 test crops, we were able to classify 81% cases that were present in the sample size. So from there, we compared the results from each of those 30 dew samples, comparing the UQ DNA-based molecular test. So that is represented in this column here. We compared those results to the results received from SRAs in field tests using the qPCR method, and compared those two sets of results to the NIR classification results from our discriminant analysis model that we had prepared. And what we found was that in 77 to 81% of the cases, the data were in agreement. So this is a really positive outcome based on that initial 30 samples that we tested using the UQ DNA-based molecular test and associating that with the NIR scans collected in the mill. So based on the positive outcome of what has been achieved so far, we are now going to be collecting far more samples. So this year we're planning on assaying 500 dew samples using the UQ DNA-based assay. We will then refine the NIR calibration model using these data and the associated scans with those 500 samples. And what we hope to achieve with the final outcome of all this modeling and analysis is that we can start exploring infection loadings within consignments coming in the mill. We can then also start exploring how crop infection loadings are and and also start mapping the incidence of the disease in our industry. And hopefully at the end of all of this, we will be able to then have that targeted approach to trying to reduce the impact of this disease to our industry. So the first two projects that we have covered, which incorporate NIR, are involving work that's been carried out in our breeding program, that being with fibre quality measurements on our SpectraCane, and then also one that's looking at disease detection in the mill. Here is a third project that's based in the mill, which has been going on since 2016. When the project started off with our collaborators, Light Solutions and Griffith University, we started off investigating the use of the Light Respect FTNIR instrument for the purpose of monitoring mill mud. And the reason we chose this instrument was because at the time it was favorable being able to scan mud samples or any samples at a distance. And the concern about trying to integrate an online system in the mill was always going to be a case of how do we do this in the mud hopper area. But as the project progressed, we also were able to incorporate the VRV MicroNIR instrument. And as you can see from the two images side by side, the one on the left being the light instrument, is quite a large, big, bulky piece of equipment. The MicroNIR is much, much smaller. It really is a tiny piece of kit, and it promises to be quite robust. So we thought we would test both instruments side by side, and both instruments actually produced surprisingly good models that were comparable. So now that it came to the part of the project where we needed to test one of these systems in the factory setting, a decision was made to incorporate the MicroNIR into our factory trial that we conducted in 2019, just purely because of the practicality of the small size of the instrument, as well as the substantial cost benefit of using the MicroNIR over the Respect instrument. So towards the end of the last crushing season, we went to the mill, and the mill assisted in installing the MicroNIR onto the mud hopper. We located the instrument just above the exit doors of the mud hopper with the hope that we could then scan the contents of the mud in the hopper that would be loaded into each truckload. So based on the mill trial, we were able to run the instrument in continuous mode. We did so over the last 3 weeks of the crushing season. And what we were able to do was actually apply some of the models that we have produced in this project on that data to start predicting some of the constituents in the mud. If you want any more information on how the models were developed, etc., I would like to refer you to the webinar that we hosted in May last year, where I gave quite a bit of detail on that work. But for now, I would like to just show you some of the findings from the trial and highlight some of the outcomes. So I thought it would be important just to show you the difference between the sort of raw data that we collect with the instrument in a laboratory setting. So this plot gives you an idea of the spread of the NIR spectra that we collected on various mill mud samples. We then apply a transformation of the data so that we can build a model from this, and this transformation that we used to model moisture in mud is based on a second derivative of the data, as well as some smoothing applied, so 3 points of smoothing per data point. And from there, we use a partial least squares regression analysis of the data against the reference values, so the moisture values that were determined on samples in the lab, to produce a model. So this is the moisture model that was developed for mud samples, and the various colors along the regression line show you the different mills that samples are included in the model from. So you can see we've got quite a nice spread across the potential moisture range for mill mud samples and from various regions within the sugar industry incorporated into that model. The problem that we encounter, however, is you know, the mill setting is not as peaceful and controlled as the lab. So where we have very nice, smooth spectra from the lab analyses of each of the mud samples, once we inserted the MicroNIR onto the mud hopper, we were faced with, you know, the challenges that come with trying to get a process from lab into an actual mill setting. So you can see that the spectra are a lot more noisy, and even once you've done the transformation, you can still see a lot more noise in the spectra. So this was a concern to us, that we would need to account for this difference compared to the data that was used to build the models. But nonetheless, I thought to show you how well those models are still able to perform to provide valuable feedback to the mills. So here is an example of one of the days where we were collecting scans in continuous mode. And this is a model that's predicting the pole value of the mud over time. And what we're seeing also in this graph are little green arrows. And these green arrows coincide with actual truck dumps that were recorded and from where we subsampled or took validation samples so that we could then test the integrity of the calibration models that we were using. One of the interesting things that came out of this trial that we conducted is more so the effect of temperature fluctuation on the modeling data. So if you look, we've recorded the NIR temperature as well as the predicted pole values along the period that we were scanning. And you can see how the temperature does have a large influence on the value that is predicted in the data. So one of the challenges going forward is to make sure that we mitigate that influence of temperature on the system. And we're working closely with the mill to ensure that we can try and do that before our trial at the beginning of the 2020 crush season. But important to show you that this sort of data can be tracked, it can be trended, and it can potentially be very useful to the mill, provided we can iron out those issues with the temperature fluctuations. So just in summary of where we're at with this project, you know, we demonstrated in 2019 that the MicroNIR certainly is a viable route for an inline mud monitoring system. The next step would be for us to advance that to an online monitoring system. So once we've established a way of leveling out those influences of temperature on the results, we are going to look at integrating that system online so that we can then get feedback through the DCS system and start trending some of those values for the mill. So trending pole values, trending fiber values, trending moisture values, etc. And just to give you an idea, once we have updated the calibration suites with all the data, so all 3 seasons data, we are getting quite good calibrations for most of the constituents we've been looking at, and we've even gotten good validation statistics in comparison to those calibration models, which is giving us a lot of promise that we we have a viable system here. Sticking with the MicroNIR, we have also been conducting some work looking to evaluate the system for an online bagasse system in the mill. So in 2019, the same sort of instrument that is used for the mud project was used on one of the bagasse mills. And this was used to provide feedback via the DCS on predictions such as pole, fibre, moisture, etc. So after the instrument was successfully commissioned and installed, we started to see how we could use this feedback data for milling train control as well as process control. So, like I said, in order to evaluate the success of a system, we have to check it against validation samples. So the way we managed it in this work was we checked the online prediction results against the mill laboratory data, in this case particularly for pole percent. So over the 69 days of the trial, we were very happy to see that the bagasse pole validation data agreed with the laboratory averages, and the standard differences were quite low. Similarly, we found that there was acceptable validation results with trending of moisture percent in bagasse, and likewise, we also looked at whether we could validate something like milling train pole extraction by marrying the MicroNIR pole extraction data and the Profast data that's coming in with the CAS system to see how we're performing in terms of pole extraction. And that was successfully validated against the laboratory daily averages as well, with low standard difference of 0.42 and almost no average difference. So what I wanted to show was that these sorts of trends can often be useful to inform process changes, particularly in the mill. So going forward, we want to delve deeper into the pole extraction trends that we've seen, and we want to see how these can correlate to aspects such as cane variety, cane maturity, or moisture percent on cane. We also want to see how it correlates to changes in cane preparation with respects to the incoming cane. And we want to demonstrate whether we can also use this sort of trending to monitor, to provide feed-forward information to the boiler station to either monitor if incoming bagasse is outside of the ideal range, or to inform changes around how to effectively control those changes in bagasse. So a lot of work going on in this space, and the mill is quite excited about what they could do with this sort of trending. And again, another example of how the MicroNIR can be used in process, and also gives some reassurance for the mud project that the system will be integrated online with the DCS as it has been done for the gas system. So what I have covered to this point is a broad overview of the 4 major research areas that we have at SRA, which is incorporating NIR. In the first instance, the projects look at enhancing existing NIR calibrations or systems with new calibration models for our SpectraCane or for our CAS system to determine RSD. But in the other 2 projects, we're looking at how we can incorporate new technologies which will help inform process improvements as well as efficiencies through online monitoring. In fact, it is because of the development of instruments such as the MicroNIR that we have been able to incorporate NIR more and more into processes. And it's because of all the advancements that have happened in the area of NIR technology. So these include, fast acquisition of software, superior processing of software. We've also got miniaturization of the electronics, which is allowing these units to become smaller and smaller, and thus easier to integrate into the mill systems, or for it to be portable even. And all of this with the benefit of these systems being cheaper, yet as accurate as their predecessors. So, of course, these advances have opened up opportunities in many other industries. And I wanted to explore what other industries are doing to see what else it is that we could be doing in our industry to also capitalize on these improvements and these advances. So if we think about someone like the pharmaceutical industry, requirements and regulation around analyses are far stricter than in the agricultural industry, for instance. And they have managed to use one of the MicroNIR pieces of equipment to actually discriminate and verify 19 different raw materials that are used in their processes. So it just shows you that a small little piece of equipment like the MicroNIR can be used because of the high quality integrity of the data that can be produced. So I just wanted to highlight that to show you that even this technology is being used in the pharmaceutical industry. But bringing it closer to home, there's been some recent research in the Australian wheat and barley industry. And this article was published in February this year, where the researchers were looking for a cost-effective in-field NIR device that can be used to predict nutrient levels in real time in the growing crops. So what these researchers did was they deployed 35 of these NIR instruments into the field, and they're not really much bigger than the size of a deck of cards. They're quite small. And they sent these out, and for 3 years they were monitoring the nitrogen levels in crops over the seasons. And what they're aiming to do is basically develop a very user-friendly way for someone with a device to connect to that device with their Bluetooth on their smartphone, and then get a prediction result within seconds on their phone to inform them of the status of the nitrogen in their crop. And then that would help them have better management of their fertilizer application, and that would help improve efficiencies and profitability for that industry. So the thinking is that we certainly could use this sort of technology in the sugar industry. So yes, those take-home messages from that research was that, yes, they could use these cost-effective instruments for this in-field real-time estimation of total nitrogen, and that this would help optimize fertilizer application. Then another project or another research article that I had a look at, which I thought would be quite applicable to us, is whether we could use in-field devices to predict CCS levels in the maturing crop, because that could surely help optimize our harvest schedules and then also help maximize our profits. So in 2013, the Japanese had actually done some research in this area using the handheld MicroNIR gun. And believe it or not, they were actually able to measure pole in whole stalk cane using this NIR gun, and and measuring this in stalks of up to 32 millimeters diameter. And they took it a step further, and they actually monitored the pole levels in the maturing cane for a number of varieties, and were able to track when would be the optimum time for harvesting in those varieties. So I certainly think this is something we could consider going forward, and something I would encourage everyone to start thinking about using. Because, you know, this whole concept of taking the lab to the field is a great one. I think if we could even have little handheld devices in the mill, you know, and have your lab in your pocket and be able to scan something in the mill, it would be so great. And the best thing about the MicroNIR range is that all the calibration models developed are transferable between the different units. So whether it's the models that are used on the mud calibrations or the bagasse system, you could put that onto the handheld and be able to do spot checks for those parameters as you're going around the mill. But you can also get accessories which allow you to measure liquid samples. So you could even expand the capability by looking at measuring liquid samples in the mill, or looking for monitoring pole losses to wastewater, for example, or in your boiler water, for example. So there are many opportunities there where we could start looking at how we can use handheld devices in situ to give us on the spot information. But ultimately, what I hope to have demonstrated today is that with the use of something like the MicroNIR, which offers a lot of flexibility and applicability to the research that we're doing, that we've had a lot of success. We've used the MicroNIR for the online bagasse system. We're now looking at using it for online mud system, and next season we're also looking at using it for a online raw sugar system and to build a new SpectraCane. Ultimately, it's the benefits due to the advances in the technology that have led to a whole lot of instruments becoming available that are far more cost effective, and they're much smaller, so they're easier to integrate, and they can even be portable. So I really do believe that there are many more opportunities to tap into. So the main question I would like to ask you then is, considering all of this, how do you think real-time monitoring could help you? How could something like this help you improve your process control? Or how could it help you maximize your efficiencies or reduce your losses, and ultimately to improve your bottom line and increase your profits? So of course, this sort of research wouldn't be possible if we didn't have funding. So of course, acknowledgement goes to the RFU for this funding, and also to the various collaborators who have been involved on the different projects. And of course, a big thank you to the staff at all the mills. If it wasn't for you, of course, this work would not be done. So, you know, we always appreciate your enthusiasm and willingness to assist, particularly, you know, the staff members at Tully Mill for assisting with the MicroNIR work, as well as at the South Johnston Mill for their participation in the RSD work. And then, of course, to Sam and Jeff and all the folk at QUT for organising a webinar such as this. And then finally, to everyone who's listening today, I really do appreciate your time, and I encourage you to get a hold of us if you have any ideas, and let's see how we can incorporate more NIR into our daily routine. Thank you.
Thanks so much, Heidi. We do have a couple of questions in the Q&A for you. So this is a bit earlier in your presentation when you were talking about the projects. Jay Venning has asked,
yeah,
what do you think the NIR is fundamentally measuring to allow a valid calibration?
It's a really good question, Jay. And the magic of NIR is that you're not measuring any one particular chemical response. You're measuring the whole matrix. So any one change in any one constituent changes the matrix very so subtly. And it's the power of the chemometric tools that are used to pick up any of those subtleties in the data or in the scans, which can then be correlated to the reference values that are pinned against the calibration. So in some instances, yes, it can calibrate really well. There'll be a very strong response. In other instances, not so much. That is the trick in trying to get as much sampling done to build these calibrations so that you can incorporate, the strength of that change, if there is a change, and then how that relates back to the real or the reference value that you've measured. So it's a good way of predicting the value, and in some instances it can be very accurate, as we've seen in the pharmaceutical industry.
Thanks, Heidi. We have a question from Andrew Dougal. What is the time frame? Could we potentially let harvesting contractors know that they are harvesting an infected field before they finish?
That's a very good question, and I would really have to bounce that off the team to give you some sort of indication of time frame. For now, the main focus has been to see whether we can or can't use this as a tool for detection, and it is quite positive. So the next step would be to see, well, how do we use this data? And one of those outcomes would be, how could we use this data to help the industry? And that would be one of the things we would consider.
Thanks, Heidi. Jay Venning has asked, what level of precision is required to reasonably fit the fibre quality assessment box?
Oh, very good question. And that's something I'd have to go and look back at, and I'm more than happy to get back with you, Jay, on that. But of course, the fibre quality parameters, one of the reasons we did the reproducibility study on the impact resistance was to understand exactly that, what is the error in the actual reference method, because the NIR can only ever be as good as the reference method. It cannot be better at predicting. So certainly if you wanted more information on that, we can get that to you. But as for the impact resistance results, we found that a standard error of 0.1 existed in the lab data, and with the calibration that we produced for the 2019 data, it was a 0.09 error.
Thanks, Heidi. Question from Andrew Dougal. In
Yep.
Cane Connections newsletter, it was mentioned that we can measure calorific value. Could you please expand on this? I hope I've said that correctly.
Okay, so I'm assuming you're referring to the bagasse analysis system, in which case, yes, we are looking at how we can also start trending calorific values. I believe there is some work going on in that space where we are doing reference analyses, looking at parameters such as ash to incorporate, but most certainly we are moving in that direction where we can get that sort of data out of the online system as well.
Thanks, Heidi. David Moller, Heidi, interesting talk. Any comment on the relative influence on temperature for the MicroNIR on the final bagasse versus the mud measurement? Is it just that the temp is more stable in the final bagasse?
Okay, we actually had a lot of difficulty trying to work around the temperature stabilization issue, and we had a higher level of temperature to deal with the bagasse system. So although it was more stable, it was certainly much higher. We were working at operating temperatures of about 70 degrees, which is unacceptable for the instrument. You're going to wear out the lifetime of that instrument very quickly. It should be operating below 40. So a number of steps were taken to try and reduce the temperature effect on the instrument. And with the trial last year, it involved using an extension probe on the instrument to move it further away from the heating surfaces at the mill. It involved using some insulation to try and reduce the transfer of heat as well. And then they've also installed a vortex cooling system around the number 5 mill bagasse setup so that they can try and get the temperature right down. And they've managed to get that right down to within the acceptable operating temperature range. And that's what we're going to try and replicate on the mud system with the upcoming trial, to try and reduce the temperature flux there, which was much lower. We had maximum temperatures of about 56 degrees. So we need to try and knock off about 20 to be within acceptable limits comfortably.
Thanks, Heidi. David Pickering asks, has any work been done on online molasses poll being done? Is it feasible?
Is it feasible? The biggest challenge that we have with the mud system is how dark the mud matrix is, and NIR does struggle a bit when you do have dark substances, and of course molasses is one of those. We do have a molasses monitoring system in one of the mills which uses NIR, and we would certainly look at using the MicroNIR for that sort of application going forward, considering the success we've had with the models developed on mill mud, which is also dark like molasses. So it's certainly an area that we could look at where we could determine pole with NIR, potentially with MicroNIR as well.
Thanks, Heidi. A question here from Phil Woods. The level of validation measures is critical for accuracy and economic assessment. What are the expected levels of validation measures?
Okay, so we're using a statistical means to test the error of prediction against the calibration model. So, trying to get those within the error control limits that are determined from the calibration model. The biggest issue, of course, with all these things is that, everybody wants values accurate to 3 decimal points. And with a system like NIR, you're getting an estimation, and an estimation is sometimes all you need to track a change. So you're within your control limits and everything is fine until you get a spike. And when you trend that spike, you're going to want to know why, and then that can be used to problem solve. So, as long as we're building calibrations and we are validating against those calibrations that are well within the error control limits, we have a fair degree of faith in the data that is being generated, and that data, if used for tracking purposes, is certainly more than good enough for process control and efficiency reasons or purposes.
Thanks, Heidi. We have a question from James Wallace. There are a number of new instruments you have discussed. How does data gathered for predictions on other instruments relate? Does the previous work need repeating before getting reliable data?
It's a very good question. There are ways and means in which you could try and transfer an existing calibration model onto different equipment. There are ways in which you can interpolate the data, etc. And that could be used as a basis model to start your new prediction calibration. You would always need to then start building up using that system and scanning new samples on that system to make that calibration applicable to that system. But of course, you could always start off with another system's calibration to then kickstart your new system. And that's also why we're trying to stick with one platform in terms of the MicroNIR. And because they've got multiple different instruments in their suite that all use the same technology, transferability is going to be so much easier. But if you're going from an FT-NIR system to a linear variable grade system, you may find that it's going to be difficult to try and transfer those models, and a lot more work will need to be done to get them acceptable on your new system.
Okay, thanks very much, Heidi. That's all the questions we have at the moment. Thanks everyone for being really interactive with the questions. Thank you all for attending our 4th and final SRA and QUT milling webinar. We hope that you found it of value and are keen to get feedback from you. You will shortly receive a link to a survey that we would like you to complete. It will only take a few minutes of your time and it will allow us to improve our webinars in the future. Tomorrow you will receive an email with the recording and the slides. Please go to the SRA webpage to see recordings from our previous milling webinar series. And this concludes our milling series for 2020, and I look forward to assisting with our 2021 program, hopefully in person. So thank you. Thanks everyone for coming along today.
Thank you.